Math 1314, section IC1, spring 2022, Tyler Junior College, homework 9.1/9.2, inverse functions, exponential functions. Video 3, exponential functions and their graphs. Now, you'll probably notice by the time this video is over and by the time this homework is over that these videos don't seem to have anything to do with inverse functions. In other words, we're suddenly talking about a different type of function called exponential functions. What happened to inverse functions? The truth is, the reason this homework covers two sections, 9.1 and 9.2, was for the sake of brevity and for the sake of time, since we're getting close to the end of the semester. And normally there would be separate topics. But in the next homework, 9.3, you'll see how they're joined together to introduce a new type of function called a logarithmic function. But let's not worry about that right now. Let's talk about what an exponential function is and what their graphs look like. Now, it's probably fairly obvious that the root word of exponential is exponent, meaning that this has something to do with functions that have exponents, and you would be correct. An exponential function is a function whose variable is only in the exponent. Now, all three of these functions are not exponential functions. They all have exponents, but only one of them is an exponential function. The first function is f of x equals x to the second power. The second function is f of x equals 3 to the x plus 1 power. And the third function is f of x equals x squared times e to the x power, whatever e is. We'll get to the e in a moment, but for now, I'll just tell you it's a number like pi. It's just a symbol that represents a number. We'll talk more about that in its own video soon. So which of these do you think is an exponential function based on this definition? Is it the first one, f of x equals x squared? Well, no, it's not an exponential function. And the reason is its variable is in the base, not in the exponent. Just a little bit of vocabulary. When you have something with the power on it, something that has the power is called the base, and the number up in the power is called the exponent. Exponent and power are somewhat synonymous. There is a subtle difference between the two, but for our purposes, we assume that they mean the same thing. But the problem is the variable is not in the base, the variable is in the base, not in the exponent as required for the definition. What about the second function, f of x equals 3 to the x plus 1? Do you think that's an exponential function? That is an exponential function. Its variable, x, is only in the exponent. But what about the third one, f of x equals x squared times e to the x? Now, there are some people that would call this an exponential function. I like to call those people wrong, because the definition of an exponential function is a function whose variable is only in the exponent. This is not an exponential function. Even though it has a variable in the exponent, this variable right here is in the exponent, it also has a variable elsewhere, namely in the base of this factor. So to be an exponential function, your variable must be in the exponent and nowhere else. Now, let's talk about the graphs of basic exponential functions. And what I mean by basic is you've got a number for the base, and you got an x on it as an exponent, and that's it. Now, there are some varieties of exponential functions, but we're going to start small. And to be honest with you, we're not going to dwell too terribly long on graphs of exponential functions. This is mostly for time issues, time reasons. All right, so we're going to start with f of x equals 2 to the x power. And we're going to graph this by using old-fashioned graphing technique, which is stick some numbers in, spit some numbers out, plot the points, and connect them. So I've already got a table set up where we're going to substitute the values from 3. It was supposed to be down to -3. So give me 1 second to insert a -3 here and just stretch this vertical line down just a little bit more. There we go. All right, so all we have to do is put these numbers into our function and see what answers we get. Let's start with 3. If I put 3 in for the exponent, I'll get f of 3 equals 2 to the third power, but this just means 2 times 2 times 2, which is not 6, it's 8. Think about it. 2 times 2 is 4 times another 2. 4 times 2 is 8. So 3 is the input, 8 is the output. And this goes along pretty easily for a moment. F of 2 is 2 to the second power. Remember, we're putting the the input in for the exponent on a 2. 2 to the second power, of course, is 2 times 2, which is just 4. Piece of cake. What about f of 1? Well, f of 1 means 2 to the first power, but that's just 2. So this is going along pretty easily. And if I were to ask you to look at the answer, the outputs that we have so far, 8, 4, and 2, and ask you to predict the next output, you probably could. Because what pattern is going as we move downwards? How do you turn 8 into 4? That also turns 4 into 2. Hint, it's not addition or subtraction. If you divide the 8 by 4, you get 2. If you divide the 4 by 2, if you divide the 8 by 2, you get 4. And if you divide the 4 by 2, you get 2. So moving downward in the second column, it looks like this is a divide by 2 pattern, which makes sense because when we're actually doing these problems, the smaller the power, the fewer 2's we have. So we divide off one of the 2's. Well, if we continue that trend, what do you think the next number in the second column is going to be? Well, if it's truly a divide by 2 pattern, 8 divided by 2 is 4, 4 divided by 2 is 2, 2 divided by 2 is 1. Now, that is the correct number, but there are some people that will balk at that because what they'll do is they'll say, okay, I'll put 0 in and I'll get 2 to the 0 power. And when they see this expression, one second, I'm trying to get something set up and it's not cooperating. When people see this expression, their brains want to say that's clearly 0 because you're not multiplying any 2's. But I'm not saying 2 times 0. I'm saying 2 to the 0 power. Is it equal to 1? Well, a real quick check in a calculator can answer that. Here's my calculator. We're going to raise 2 to the 0 power. My exponent button is this one next to the 7 that says x to the y power. 2 exponent 0 equals, and it agrees with me that it's 1. Now, there's a multitude of reasons why 2 to the 0 power is equal to 1. In fact, we can say something a little bit more general than that. We can say the following. As soon as I get this formatted the way I want it, we can say for any base b that's not equal to 0, let me go grab a not equal sign. Got it right here. Just got to copy it and paste it inside of the whiteboard. For any base b not equal to 0, then b to the 0 power is equal to 1. Now, I can't type the exponent there, so I have to do some formatting shenanigans. Just go up here and type a smaller 0. But for any base b that's not equal to 0, b to the 0 power is equal to 1. Again, this is something that can actually be proven, but for the sake of moving forward, we'll just assume that we can take this at face value. Any number except 0 raised to the 0 power is equal to 1. And if you're going to try to break things and say, well, what about 0 to the 0 power? Now you enter the realm of calculus, and this is not a calculus class. It's called indeterminate, which loosely means it can equal anything depending how you get there. In calculus, that makes more sense. But for our purposes, any number to the 0 power is 1, except 0 to the 0 power. Okay, so what about the next number, f of -1? Well, if we put it into the function, we get 2 to the -1, and people's instincts will say -2. However, consider the pattern we built over here moving downward. The pattern was a divide by 2 pattern, which looks and is correct. So if we continue the divide by 2 pattern, 8 divided by 2 is 4, 4 divided by 2 is 2, 2 divided by 2 is 1. 1 second, folks. Sorry, folks, I had to pause and take an urgent phone call. So my train of thought got a little bit derailed, but I'm pretty sure we were talking about the pattern moving downward and the answers in the left column, the divide by 2 pattern. 8 divided by 2 is 4, 4 divided by 2 is 1. Let me try that again. 8 divided by 2 is 4. It might help if I actually highlight the numbers I'm looking at, and you can see them too. 8 divided by 2 is 4, 4 divided by 2 is 2, 2 divided by 2 is 1. And if I continue that pattern, what is 1 divided by 2? Well, if you do 1 divided by 2, you get 0.5, but that's just a half. And that would be correct, that 2 to the negative 1 power is 1/2. And if you wanted to verify that, again, you could also check it out on a calculator, which we're about to do. 1 divided by 2 is 1/2. Well, we already knew that, but 2 exponent negative 1 also equals 1/2. Now, that does not seem incredibly intuitive, so what's actually going on here? Well, the truth is, when you raise a number to a negative power, it's the reciprocal of raising the number to the positive power. In other words, 2 to the negative 1 equals 1 over 2 to the positive 1. Let me throw a box around that for emphasis, because this is how negative powers work in general. So for example, for the next one, when I put in negative 2, f of negative 2 is 2 to the negative 2 power. But to raise something to the negative 2 power means 1 over raising that to the positive 2 power, which is 1/4. And this is consistent with our divided by 2 observations over here, because if I took 1/2, which I currently have on my calculator, now you can see that too. If I take that 1/2 and divide it by 2, it's going to give me 0.25, but that's the same as 1 divided by 4. So exponents get a little bit funny when you start using negative exponents, but they are predictable. In fact, I would even go further to say the following. Did not mean to delete that. Let me fix something real quick to make sure that doesn't accidentally happen again. Text box is so wide, I accidentally erased it when I was erasing the things down here. But I think it's worthwhile to make another observation about raising any number to a negative power. So let me jump inside this text box, if it will let me jump inside this text box. It does not want me to jump inside this text box, so well, I will just retype it. All right. For any base b, and it still has to not be equal to 0, b, and I'm going to type to the negative n power equals 1 over b, and I'm going to type to the positive. In fact, I'm just going to write this part. It'll be just a lot easier. I do want to take the font size back up though, so let's do that. All right, red please. All right, so for any base b not equal to 0, we have, one second, there was something here that disappeared, I think. Nope, guess not. For any base b not equal to 0, we have b to the negative n power is equal to 1 over b to the positive n power. It doesn't seem very intuitive, but the way exponents work, it must be. Now, if you want further review on exponential functions, exponent rules, I've got a video or two that goes over them, and I'll make that available to you in Canvas. All right, so if we continue it one more time, then for example, the negative 3, f of negative 3 is 2 to the negative 3 power, but using the negative exponent rule, that's 1 over 2 to the positive 3 power. And we already know that 2 to the positive 3 is 8. In fact, you start noticing a trend over here. One second, I'm getting this ready so that I can erase a bunch of stuff without killing everything. You start noticing a trend over here. There we go. That these answers are occurring in reciprocal pairs. The reciprocal of 8 is 1 over 8. The reciprocal of 4 is 1 over 4. The reciprocal of 2 is 1 over 2. And it's a direct consequence of the negative exponent rule. All right, so now that we got these ordered pairs, let's clean this up and let's sketch this graph. All right, I've got a coordinate plane ready to go, and you'll notice that I don't have much room below the x-axis. That's because if you look at your y coordinates, your outputs, none of them are negative. That kind of makes sense because raising 2 to a positive power will give a positive answer. Raising 2 to a negative power will reciprocate a positive answer, but it will still be positive. So in other words, we don't get any negative outputs here, only positive. We don't even get 0. More on that in just a second. Let's plot these points. I'm going to put some hearts on the graph where these belong. All right, so starting with 3, 8. Well, I guess for clarity, I could number some of these. 1, 2, 3, -1, -2, -3, and then going up 1, 2, 3, 4, 5, 6, 7, and 8. And now let's put some dots in the form of hearts. Over 3 up 8 is about here. Over 2 up 4 is about here. Over 1 up 2 is about here. And on the first glance, it might look like this is a line, but watch. Over 0 up 1 is here. And now we start deviating a little bit from being linear. And as we continue to the left, we run into this issue where the numbers that we're trying to put are getting smaller and smaller. In fact, remember the pattern moving down was everything got divided by 2. Well, in the picture, that means everything is half as high as it used to be when I go backwards. So these are just cutting their height in half as we move from right to left. So that means at -1, we only go up a half. At -2, we only go up a quarter. And at this point, we're just kind of eyeballing it. And by the time we go back 3, we're only up 1/8. We're barely above the x-axis. And notice that these points, these hearts, if you will, are kind of forming this curve that looks a little something like this. On the right end behavior is rising, which makes sense. The further to the right that we go, the higher the power. So the more 2's we multiply by. So things are getting twice as high every time I take 1 step to the right. All the points are going twice as high as they used to be. But in reverse, as we move from right to left on the graph, each point is getting cut in half in terms of its distance from the ground. So will these points ever hit the ground, aka the x-axis? No, they won't. Half of 8 is 4. Half of 4 is 2. Half of 2 is 1. Half of 1 is a half. Half of a half is a fourth. Half of a fourth is an eighth. Half of an eighth is a 16th. Half of the 16th is 1/32, et cetera, et cetera, et cetera. So as long as you have something that's positive and you take half of it, it'll still be positive. It gets smaller, but it'll still be positive and never hit 0. It will just get closer to 0. Where have we seen this before? Oh yeah, with asymptotes. The left end of this graph is approaching the x-axis as a horizontal asymptote, but it's only on the left side. So I guess if it's a half asymptote, maybe. Anyway, so let's see what we can extract from this graph in general. Now, we've only got one example, but I'll tell you that the following are true as long as our base is bigger than 1. In general, if f of x equals b to the x power and b is greater than 1, I'll explain why being greater than 1 matters in this context, then the following 6 things are true about this graph. Number 1, the graph has a y-intercept at 0, 1. We saw that back here. The y-intercept was indeed at 0, 1. And it makes perfect sense because to be the y-intercept, your x has to equal 0. And regardless of the base, as long as it's not equal to 0, but if you're greater than 1, then you can't be 0, any number to the 0 power is 1. So we'll always have a y-intercept at 0, 1. But what about x-intercepts? Well, okay, it didn't say it there, but there are no x-intercepts. So give me 1 second to fix this. There we go. The graph has a y-intercept at 0, 1, but no x-intercepts. No x-intercepts because on the left end of the graph, it's approaching asymptotically. That is the correct word. It's approaching asymptotically. So it's approaching the x-axis without ever touching it. And on the right end of the graph, it just blows up to infinity. So no x-intercepts. Number 2, the graph has what I called a base point at 1, b. Now, what do I mean by that? Well, if we go back to the graph, there was a specific point of note, and that point is right here. This is what I sometimes call the base point. Now, this is my own terminology. It's not official. But the reason I call it the base point is because the y coordinate is the base of the function, which makes sense because if I put in 1 for the exponent, like I did right here, if I put in 1 for the exponent, the answer will be whatever the base is. And the reason I call it the base point is because if we had this graph and didn't know the function, but knew it was exponential based on its shape, then we can look at the base point and say, hey, this function's base, this exponential's function base is 2. Okay, number 3. The graph is strictly increasing. Oops, you weren't supposed to see all that, which means from left to right, the graph is going up. Or as the x's get larger, so do the y's. Number 4. The graph has a horizontal asymptote on the left at y equals 0. So we do have a horizontal asymptote, but it's only in the left half of the graph. Number 5 and 6 are about domain and range. So let's just look at the picture for a second. This graph goes forever to the left and forever to the right. It gets crazy steep. But I can argue that it goes forever to the right because the further to the right we go, the bigger the x is. Can you put any large number in for the exponent? For example, could I put in 16 for the x? Of course I could. I would get 65,536, which is way up in the sky. But there is a point above x equals 16, as there is a point above every single x as I move to the right. This graph goes forever left and forever right. And what does that make its domain? Well, any graph that goes forever left and forever right has a domain from negative infinity to infinity, meaning all real numbers, but not so much for the range. The range are the y values. So visually, it's bottom to top. Now, this graph goes up forever, which means the range goes to infinity, but it does not go down forever because it hits the ground, or does it? This graph gets closer and closer to the x-axis, but it never gets there. If it got there, it would hit 0 and stop, but it gets closer to 0 and never reaches it. So how can we write an interval that says I start at 0, but I don't include 0? And the answer is by putting a parentheses on it. The range is 0 to infinity. So what this means is for an exponential function whose base is greater than 1, we can put in any number we want, but we can only get out positive numbers. I keep saying if the base is greater than 1, but what if the base is less than 1? Well, we're not going to go through all the motions again, so we'll just kind of summarize it. If the base is less than 1, everything is the same except 2 things. See if you can find them. I'll switch back for a second so that you can see this list. And now switch back to this one. There's 2 changes. Base bigger than 1, base less than 1, but still positive. Bigger than 1, less than 1. Did you find the 2 changes? The 2 changes are when the base is greater than 1, our function is strictly increasing, but when the base is less than 1, our function is strictly decreasing. And when the base is bigger than 1, we have a horizontal asymptote on the left at y equals 0, but it's on the right at y equals 0 when the base is less than 1. In other words, our graph looks a little something like this. And I'm just going to freehand it. I'm not going to write all of the relevant things. The only problem is the base point, because the base point is going to be 1 comma something. But that something is so small that we really can't tell what it is. So the base point there kind of loses some of its flavor. Back here, it was over 1 up to the base is 2. Now, there is a way to locate the base correctly off of the graph of a decreasing exponential function, but I'll let you just ponder that. Hint, has to do with what happens when x equals -1.